So the way a typical class will work is you guys will hand in your homework assignments, the TGOs and example questions, and then I'll pass back the previous lecture's assignments that will be graded and handed back. So usually there's about a 4 or 5 minute buffer where I'm handing them back. By the end of the semester, I'll have a much better handle on all of your names because I've been constantly handing back your assignments. And don't be afraid to correct me if I'm getting your name wrong. I've had students, I'll go their entire semester pronouncing their name wrong, and they will never correct me, and then I'll see them randomly like, no, my name's actually such and such. Like, I was pronouncing it that way for a whole semester, like half a year. So, all right. So basically, that's the way it's going to work. So, yeah. All right. So this is where we got up to last time. We finished Mealy and Moore machines. And now you kind of use Mealy and Moore machines to build digital systems. So here we're talking about a synchronous up counter, and we have an LCD display. And so what it's using is using clock D flip-flops. And so you have a clock on each flip-flop, and it's dependent upon the previous Q output. So when you flip, you'll go D, and you go D bar, and then you go to Q. That signal will change. And the whole idea is that you go in binary up counter, 0, 1, and then once it goes to 0, the next one goes to 1, 1, 0. So one of the issues that we're going to come across here, and we're going to be talking about this situation here, is what happens when we have Q equals 0, Q equals 1, I'm sorry, Q2 equals 0, Q1 equals 1, and Q0 equals 1. Now, what happens is you'll get these situations where you'll flip, and what you're expecting to do is you're expecting it to go to 1, 0, 0. Unfortunately, what's happening is because of that, it's depending on this one to change and this one to change and this one to change. You're actually getting situations where you're going to 0, 1, 0, then you're going to 0, 0, 0, and then you're going to 1, 0, 0. So you have a couple of really brief instances where you have the incorrect values on the output. So what we're actually going to have here is a situation where we're going to get, this is what's known as a race condition. And so a lot of advanced digital systems is designing how to avoid race conditions. So we're going to be worrying a lot about this, especially when we get into design of sequential logic. So what we're doing here, we're going to first talk about this concept of gray code. So topical objective 1.13, we define gray code as a set of continuous values in a circular list where the Hamming distance is 1. So what is Hamming distance? Any idea? So Hamming distance is what you have, the number of binary values that change during any clock pulse, right? So or any number of values that change at the exact same time. So what we mean is at most one binary value changes. So for example, when you count from 0, 0, 0 to 0, 0, 1, the Hamming distance is 1. When you count from 0, 0, 1 to 0, 1, 0, you're changing that second bit and that first bit. So the Hamming distance is 2. So whenever you have a Hamming distance of more than 1, you have a potential for a race condition. So for example, I described that situation here where you have 0, 1, 1, and you're switching to 1, 0, 0. Your Hamming distance becomes 3, and in that instance, you're actually having a race condition that occurs. So the problem with race conditions is that when you have that wrong value, you have a temporary instance where you're sending an incorrect value out from your, either your, in this case, our counter. So there's this very brief moment where you're seeing, where you, instead of seeing 4, you're seeing 3, 2, 0, 4. And that's an issue. So we introduced this idea of gray code as a way to actually get around this. So here is the actual comparison of the 3-bit binary and gray code truth table. So same thing, 0, 0, 0, 0, 0, 0, increment 1, the Hamming distance is 1. When we get to 2, this is where we have our Hamming distance of 2, right? So what the designers of gray code have done is that we have 0, 1, 0. So what they've done is they've switched this middle bit, and the value of 0, 1, 1 is defined in gray code as 2. Right? So in this case, now we have 3, 0, 1, 1 in typical binary. In grade code, we have 0, 1, 1. So what we do is we just change it to 0, 1, 0 to eliminate the possible race condition. Grade code uses zeros and ones, but it is not binary per se. Does that make sense? Binary is when you have an instance where I'm getting away so you can't hear me on the computer later. But binary is what happens when you have a series of n digits, 0 through n, and the value of the binary. I'm sorry, I probably should go n through 0 condition. So 2 to the 0, or the value times 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? Grade code is a specific form of zeros and ones that correlates in this manner specifically to eliminate race conditions. So it's different. It's not binary. So this 0, 1, 1 in grade code is 2. 0, 1, 0 in grade code is 3. Does that make sense? I see some skeptical faces. Are you good? You look skeptical.
Okay, so they're trying to change one bit at a time.
Exactly. Yeah, handing distance is changing one bit at a time at most. Because we go back to our situation here. If we have this instance where we have 0, 0, 1, right? And we try to change the clock pulse. In that manner, it should be 1, 0, 0 because it's actually the opposite direction, right? So if we change this, it goes 0 and then 1, right, to 2. Now, here's what's going to happen. You send in the clock pulse again, your D flip-flop's going to change to 1, 1, 0. And in the opposite direction, that's 0, 0, 1, right? So then you send it in, you're going to go to 0. This is going to change, right? No, it's not. It's not. It's going to wait until it changes again. And that's what happens. So we calculate this out in the order that it comes to. It's going to be, I'll walk through it this way. So it's 0, 0, 0. We switch here, 0, 0, 1. Switch 0, 1, 0. And then we have 0, 1, 0. We have 1, 1, 0. We switch again, it's going to go to 0, 0, 1. Sorry. Right? So when we go back to this truth table, now it should make more sense, right? So we had 0, 0, 0. This is the opposite direction. So it's 0, 0, 0. And then we switched this one, right? And then this one got switched. And then this one got switched. And then what's going to happen? This one gets switched. This value correlates to that value. So the whole idea is to only switch one bit at a time. Now this doesn't just work well in digital flip-flops and sequential elements. Now, how many of you are familiar with the problem of the towers of Hanoi? Okay, so 1, right? So the general idea is that you have 3 outplates and you have 3 different sizes. So you have 3 here, and you have to move them around. If you use grade code, it matches perfectly. 1, 1, right? And then you start moving it back here. If you do that, if you follow that direction and you follow this grade code perfectly, you'll eventually get all 3 of them, and that's the optimal solution. So using this actually has outside applications as well. But in our course, and so here's for any bit, I actually included, this is not a TGO, but this is a little trick. You just construct a 1-bit list, then you reflect on it, append zeros and ones, so you put zeros on there, reflect, append zeros and ones, and reflect. So what that means is 0, 1, 0, 1, 1, 0, and then 0, 0, 0, 1, 1, 0, 0, 0, right? So that's how you actually build a full grade code for any number of bits. So as I mentioned, Towers of Hanoi is a value for grade code that you can use. Also, genetic algorithms. Due to the Hamming distance properties of gray code, they're sometimes used for genetic algorithms, so you only split one element of the DNA. And Karnaugh maps. And this is where it becomes important. You guys you've taken digital systems, so you know Karnaugh maps, right? So gray code is how we solve using Karnaugh maps. And so let me scroll up here, give you the definition of Karnaugh map and min term and max term. The Karnaugh map, which we'll commonly call K-map, is a pictorial method used to minimize Boolean expressions without having to use Boolean algebra, theorems, and equation manipulations. So when you get to a certain point where Boolean algorithm theorems and equation manipulations get prohibitively large, you can use these K-maps to significantly reduce the amount of work that you have to do. And so we'll describe precisely how to do a K-map in a second here for review. But these are two important terms when defining a Karnaugh map. A min term and a max term. A min term is an instance of the function where the output is 1, and it's shown symbolically as lowercase f equals the summation of m of I. So lowercase m of I, that means min term, right? So if I were to give you this, if I were to ask a problem as a function of equals 0, 1, 3, 4, and 6. Those are the instances where the function is 1. So this would be a 3-bit input where you'd have 0, 0, 0, 0, 0, 1 is true, 0, 0, 1 is true, 0, 1, 0 is false, 0, 1, 1 is true, 1, 0, 0 is true, 1, 0, 1 is false, 1, 1, 0 is true, and 1, 1, 1 is false. So that would mean our max terms, which are our next portion of the definition. A max term is an instance of the function where the output is 0. It is shown symbolically as f equals the multiplier of uppercase m of I. So our max terms are going to be, here we'd have 2, 5, and 7. So these would be our min terms, and these would be our max terms. And so we end up using these in order to reduce my truth table into this pictorial method. It's the wording I used. And when you set up the truth table, so here we had a, while you guys are jotting this down, I'll draw it up here. So typically you'll have A, B, and C, right? And you'll go like this. And so you'll use gray code to count down the binary values here. So you have 0, 0, 0, 1, 1, 1, 1, 0, right? Same thing, then you'll have 0 and 1. And then what you'll do is you'll fill out the truth table using your min terms and max terms. All right, so I gave this example of the truth table. I've defined my min terms here. These are the min terms, so this means 3, 5, 6, and 7 are 1. And this symbol is the max term. That means my max terms are 0, 1, 2, 3, 4, right? And so what that means is what we're going to do, you can do it one of two ways. So you can either do A, B, or C, and you do 0, 0, 0, 1, 1, 1, 1, 0 to reflect the gray code, and then 0, 1, and then you find where your min term is. So 0, 0, 0 is 0, 0, 0, 1 is 0, 0, 1, 0 is 0, 0, 1, 1 is 1, 1, 1, 0 is 1, that's this guy, 1, 1, 1 is this guy, so it's 1, and then you have 1, 0, 0, which is 0, and 1, 0, 1, which is 1. So this is your Karnaugh map when you do it that way. other way you can do it, which is the way I've put into the notes, where you have A is the lone variable and B and C are your are your combined. As you can see, I've once again stuck with the gray code. So, and then I followed the min terms and max terms, 3, 5, 6, and 7. As you can see, 0, 1, 1 is 3, 7, and that's 6 and 7, and that's 5. So what happens is you can start seeing these patterns where everything kind of groups together, right? When you start seeing these patterns, that we're going to use those to be able to reduce our function, or be able to determine what the function is. So for example, here, when A is 1, so you can actually use A, and then you can actually look at it. We see this common, this is, B or C is the case, or A naught, B, C, right? And so this is a concept, we're going to go into this a little later, known as Shannon expansion. Is anybody familiar with Shannon expansion? The idea of Shannon expansion is that when you have a binary value, you can break down any of these functions into a subset where one of the variables is 0 and you have an equation, or when the variable is 1 and you have another equation. So that's what we've done here. We have our Shannon expansion of when A naught is equal to B and C, or A, B, or C. So that's how you're going to use the Carnot map to be able to derive a simpler equation. Okay. So, for example, I have this question about Carnot maps, equation 1.3. Given the following, use a K-map to derive the input function. So we have our min terms. We have our four variables. You can tell this because it goes up to 15, right? So our min terms are 0, 2, 4, 5, 8, 10, and 12. And our max terms are 1, 3, 6, 7, 11, 13, 14, and 15. So when we take this is the K-map that we derive. I've combined A and B on the y-axis and C and D on the x-axis. 0, 0, 0, 1, 1, 1, 1, 0 using gray code. And we have filled out our truth table 0, 1, 3, and 2. Oh, no, I'm sorry. Oh, yeah, it's the other way around. So 0 is a min term. 1 is a max term. 3 is a max term. 2 is a min term. Right? And we go on from there. And so I'm going to describe how we come up with this. But basically, when you take these, make these blocks, and we'll describe what these are in a second, you have to make them in multiples of 2. So you can see here that I have done an instance where I have this red box here, right? And so this is a case of C and D is always true, no matter what. And then you have this case, this blue box here, that is equal to A naught, B, C naught is always true.
Isn't that C naught, D naught?
Yeah.
C naught, D naught?
0, 0, 1.
No. Look at the blue box.
No,
No, the one before that.
C naught is true in both cases.
No, the one where you're doing the group.
Oh, yes. C. Okay, C. Oh, I see. Yes, C naught, D naught. Yes, that's correct. So in one case, you have C naught or D naught, which I have screwed up while saying that, but I've fortunately correctly written on the answer right below here. C naught or D naught is one of them, right? And so we've come up with this other, the blue box is A or A naught, B, C naught, right? And then the other one here, 1, 2, and you can actually combine these all into 4, right? and that comes out to B naught or D naught. Okay, does that make sense? Awesome. All right, so here I want to talk about how we're going to use K-maps to formally avoid these race conditions. So let's formally define race condition. A race condition is the behavior of an electronic or software system where the output is dependent on the sequence or timing of other uncontrollable events. So we were talking about that situation where we had 0, 1, 1 in our synchronous up counter. And our third D flip-flop is dependent on the second D flip-flop and is dependent on the first D flip-flop. So the D flip-flop cannot control the outside inputs. So its inputs. It only takes what its inputs, performs the operation, right? So we were talking yesterday. We were talking about finite state machines. The D flip-flop's a finite state machine, right? Well, it can only take, its input string, compares the input alphabet, performs an operation, compares to its memory element. So it's a Mealy machine, puts it on the output. But if the input's wrong, it's not the D flip-flop's fault. So in this case, since asynchronous sequential circuits do not have discrete timing signals, we actually have to design the circuits in a way to relegate their operation. You can mitigate this some with synchronous circuits using clock signals, but as we saw in an example earlier, that's not always going to be the case. And I made this big note here. Bearing this in mind will save you lots of time of coding projects in this course and the rest of your career. The reason why? Because you're going to get outputs on your coding project and they're going to look weird. You're going to, what? If you properly design, come up with a good design flow, lay it out properly, then you'll actually have a very good memory element. Okay. So let's describe an example of how race conditions are applied in K-maps. TGOs race conditions are easy to spot using Karnaugh maps because race conditions may exist when moving between any pair of adjacent but disjoint regions circumscribed on the map. So let me read that again, and then I'll give, in example 1.4, we described an example of a disjoint region. Race hazards are easy to spot using K-maps because a race condition may exist when moving between any pair of adjacent but disjoint regions circumscribed on the map. So what do I mean by disjoint region?
Regions that don't connect to each other.
Correct. So in this example 1.4, where are my disjoint regions?
Blue.
Blue is one, and what's the disjoint with?
The red.
The red. No, not the red.
The green.
The green. Why is it the green and not the red? Go back to the definition.
Adjacent.
Yeah, they have to be adjacent but disjoint. So in order to do that, we're going to show how to eliminate it, and the typical way to do it, we're actually going to show this in a couple steps. You connect them somehow with another region. And if you notice, these actually connect. So our two steps of the problem will be to actually take care of that. So in example 1.4, we have a K-map, find any race conditions, that's part one. Describe how they may be eliminated by drawing an updated K-map, eliminating the hazards, and stating the updated function. So when you take any of my quizzes or any of my exams, follow it step by step. I'm usually I try to be very clear in what I want in the problem. So given the following K-map, here's your following K-map. First, find any race conditions. So that's where we're knowing the definition of race condition is and how it's used. How do we use race condition in K-maps? You guys just went over the TGO that answers the question.
Adjacent but disjoint.
Adjacent to disjoint region. So where's my race condition?
Blue, green.
Yep, blue and green, right? So you go race condition. So technically, you can also say there's a race condition here between blue and red because they're joint this way, but the one I really wanted you to notice is here. I'll accept both of those on an exam.
Is the red box adjacent to the blue box?
Yes, that's a very good point. They go around. Yes.
With the red and the green, the top right red and the green bottom right.
Oh, no, you see how the red and the green overlap?
Yeah.
So they are not disjoint.
Okay.
Once they're not disjoint, that eliminates the entire region. So here, I see what you're saying. So this is a good nuanced question. So here we're talking about this red here and this green one here, correct? So the reason why they are not race conditions is because once the region covers any part of the other region, they are no longer disjoint. So that's where the definition is. So I believe the question is this part disjoint?
So the top right,
Yeah.
the box and the bottom right. Yeah.
No, this is still, this is all great.
Okay.
Yeah, correct. So, but it's important to notice that, and we'll actually go over an example of later in this example, that they go around. So these are disjoint next to each other. Yes?
The red and blue are actually race conditions.
Yeah.
Even if you use the solution to the blue and green race condition, the blue and green would still be a race condition.
Correct.
So when
Just so let me finish the problem.
All right.
That you're noticing the thing I wanted you to notice. So, all right. So hold on to that thought, and when I ask the next question, say that again. Okay. So what we have done here. So basically, I've just said if we are at state 111, move to 110. Basically, this all describes what you've just said. I have created this new disjoint section, right? I've created this new section to overlap blue and green. And remember, they have to be in multiples of 2. Regions with K-map must have a square multiples of 2. So, what is the issue with what I've just done?
The blue and green are still race conditions.
Bingo. Right? So how would I get around that? I'll give you a hint. Your regions have to be multiples of 2. And what's the other thing who was just asking me about that they wrap around, right? So if they wrap around, what could I do? Who said that? Correct. Bottom and top. So what we would do is you would just go like this. And that's one region. So now we've overlapped blue, we've overlapped green, and we have one region. This region here, we've combined the blue and the black. That's now one region, right? And that's going to be that's A, right? And so it's going to be everything except C and D, right? So you can come up with another way. C and D not is one way we could describe that region, right? There's multiple other ways. So then this green region is, what's that green region? AB not. And then what's our blue region? Just CD not. So very good. You guys noticed all the little tricks I put into this example question. Yes?
Does every box have to be touching each other, or do they all just have to be connected?
They have to be connected.
Okay.
So if they're touching each other like this, like here this blue one was touching this green one here, that's adjacent but disjoint. So it has a race condition. So if I'm asking in the problem, if I state find any race conditions, I want you to take that K-map and eliminate the race conditions. So let me ask you this question. So we had this AC naught, AB naught, or BCD naught, right? And then we come up with our race conditions, and what happened to that equation? It got expanded, right? So when you have an expanded equation, how does that apply to the actual circuit? More complicated, right? So we've now created a more complicated circuit, which consumes more power, and so has slightly higher area, right? So those are drawbacks, but what's our positive? No race conditions, right? So that's when, up to this point in your career, you're just going to start working in electrical circuits about trying to minimize designs. A good design requires good compromise. And so in this case, we've made a design compromise. We have compromised area for a guarantee of elimination of race conditions. So that's why doing this problem is important. Right. And so basically, you guys point everything out, and now you have the right answer, right? C or not or D not is another way of saying C and D not. So, okay, so does anybody have any questions? We've kind of done some fundamental stuff. In section 3, we're going to be applying K-maps to designs of more complex sequential elements and finite state machines. Okay, so next, I want to kind of go briefly into what a computer architecture actually is. So if you look at the syllabus, students will be able to know the architecture of a basic computer system. In this course, we're using the Pedersen-Hennessy textbook, and we will learn an architecture called MIPS. We will go into a lot of detail about that today. Objective 6, know the operation and components of a basic computer system, including control, arithmetic processors, registers, buses, memory hierarchy, cache, and virtual memory. And objective 7, know the relationship between the hardware architecture and a computer's assembly language instruction set. So what you're going to do is you're going to take a basic C element of C code, and then you're going to convert it to an assembly language, and then you're going to convert it to a machine language, and then you're actually going to put that in a text document, upload it into your C code. It will initialize the instruction memory and data memory, and then you will actually run your computer, which you have coded in C, to run the operation. So you actually be able to physically know precisely what the code is doing. So in order to do that, I want to go over this quick little diagram here. The hardware of a computer, I'm going to zoom in really quick. I know the TGO there for instruction set architecture is there. So the whole idea is that you have some sort of memory element, and we're going to be talking about memory hierarchy, virtual memory, cache memory, and non-volatile memory later in the course in section 5. So you have some sort of communication, direct memory access, which then creates an instruction. The instruction, in this case in MIPS, is 32 bits. Your control, the control signal is known as an operation code, or an opcode for short. The 6 bits of those 32 goes to your controller. The rest of the values go to the data path to be operated on. We're going to go into a lot more detail on this course. Performs the operation. You perform on these local copies of registers, which are very fast, or dual read, single write SRAM. And then, once you're done, you want to put it back to the output. So the thing that does this is what's known as an instruction set architecture. In short, it's an architecture that performs operations on instructions. So specifically, we'll define it here as a set of assembly language instructions to provide a link between software and hardware. So now you've coded in, you're going to code in C. It's going to change it to assembly language, like we were talking about on Tuesday with Dennis Ritchie, being able to take that code, convert it to assembly language, and converts it directly to machine language, which improves performance. So now you're linking software and hardware. So here I want to read this quote from Henry Petrosky. The most amazing achievement in the computer software industry is that continuing cancellation of the steady and staggering gains made by computer hardware industry. What he's saying there is, Man, the computer hardware industry, they're coming up, they're meeting this Moore's law, they're making these computers run fast, and we cancel that by writing garbage code. So in this course, you're going to learn how to not write garbage code. At least that's the goal. So given an instruction set, software programmers and hardware engineers can work essentially independently. The software engineers will develop code that compiles down to the assembly language, and the hardware engineers are going to design a hardware architecture that implements that assembly language by translating the assembly language in machine code. So if you have that instruction set architecture, you can have them work as independent teams. So instruction set architectures are typically designed to extract the highest possible performance, and we'll discuss that later in this section, specifically in a concept known as Amdahl's law. And it defines registers, data transfer nodes. We'll learn about load word and store word instructions, memory and I/O, and these four types of instruction set architectures. Reduced instruction set computer, which is the MIPS is a reduced instruction set computer. It's appropriate in a sophomore, junior level electrical engineering, computer engineering course to introduce to your hands on a RISC program. It's complicated, but when you deal with it at it's better than dealing with complex instruction set computers, which allow for more programs. The reduced instruction set computer, the goal is to perform the operation as few unique types of instructions as possible. Now then you have very large instruction word. You can have 64 or 128 bits. And then superscalar is a form of instruction set architecture that takes advantage of pipelining. And so next I would like to formally differentiate between assembly language and machine language. Assembly language is a symbolic representation of machine instructions, and machine language is the binary representation of machine instructions. And so I've given an example here where assembly language, what this means, add S2, S1, and S3, these are register values in the data path. And what we're doing is we're adding these two values and placing the value in this register. So I've commented it, you will see S1 plus S3 is equal to S2. And what we'll learn is what that happens is we have values coming out of the registers. They're going into the arithmetic logic unit, and it's coming out, and it's going to circumvent the data memory because we don't want to put it there because that's a slow operation, and it'll put it right back into a register. Now the machine language is actual binary representation of this. So here we have a 32-bit value. The first 6 bits are the opcode, like I was telling you. In R-type MIPS data path, the binary value is 6 zeros or 0 hex. And then there are 32 registers in MIPS. So the next 5 bits are each representing one of the registers. Right? So that's S1, S3, yeah, S2, S1, and S3, right? And then these next 5 are shift amount, which we'll learn about later. Basically, we want to have a 32-bit value to be able to shift a number of bits. Remember, if you shift a binary bit left 1, what does that do to its value? If I have 1, 1, and then I shift it left so it becomes 1, 1, 0, what does that do? It's specifically by what?
2.
By factor of 2, right? Yeah. So it becomes 3 and then 6. So if I have 7 and shift left, it's 14, right? And then the last 5 are what's known as a function. Remember this, all the R-type values, which are take the value 2 registers, perform some sort of arithmetic operation, and store it in another register, just like we have here. 2 registers, we have added, and we store. These last 6 bits are the function. This last 6 of 20 hex indicates add. And we'll go into a lot more detail of that in section 6. So know the relationship between hardware and computer assembly language. All right, so TGO 1.20, computer architecture and computer organization. I can tell you the wording of the TGO. Define and differentiate between computer architecture and give me 3 examples of each. Computer architecture is system attributes of computer which contribute to its logical execution and are visible to the programmer. And here I've given the instruction set, data representation, like we've just shown you, 32 bits, I/O mechanisms, and memory addressing. What we mean by visible to the programmer is you can write code that manipulates its operation. Computer organization is physical details of the computer that are transparent to the programmer. And when I say transparent, what I mean is that it's there. You know, if you take the computer apart, you can see it, but that does not mean that you can actually write any code that manipulates it. So control signals, anything coming out of the controller going through the data path, you cannot actually physically manipulate those with code. You cannot implement the memory technology. So memory addressing, you can actually write code that tells where to store the memory, right? But you can't actually physically change the memory with code, right? So system attributes of computer that contribute to its logical execution and are visible to the programmer. I mean, you can write it in there. Hardware implementation of an instruction, control signals, memory technology, and then ALU, CPU, computer designs. Okay. Does anybody have any questions on that definition? All right, I'm going to scroll up past computer architecture because I want to read this expert comment. All right, so Dr. Ranganathan was my major professor at the University of South Florida. I will read you what he said, and then you'll understand why I consider this to be so important. I had a student interview at Intel. This is another student who was a couple years ahead of me, or a few years ahead of me, and they asked the difference between computer architecture and computer organization. The student didn't know, and they cut off the interview immediately. And so he vowed, never again, I will never have that happen to me. So the first question on his first exam and the first question on his final exam were define and differentiate between computer architecture and computer organization and give 3 examples of each. And so you probably noticed I was able to say those definitions without looking at the screen verbatim. So what do you think the first question on your exam 1 is going to be? That, right? Define and differentiate between computer organization. Yeah. Do not want you guys going out to a interview where I know they could potentially ask the question. So let me ask you a question. From Intel's perspective, why would having a person know the difference between computer architecture and computer organization be so important that if they didn't know it, they just end the interview immediately? Bear in mind, this is a PhD student, so this is somebody who definitely should know this, or at least be able to venture a intelligent guess.
Intel is a company that makes hardware.
Mm-hmm. And they also design instruction sets.
And I guess they pretty much do those 2 things.
Mm-hmm.
And so, if, depending on your job, you could go with either one of those, maybe both.
No, you can do both, but you're right. That's pretty much Intel either does computer architecture design or computer organization design, right? So computer organization design is that underlying technology. We're going to VLSI. It's transparent to the programmer. You should be able to know when you're writing code what you can manipulate and what you cannot, right? So this is another thing. This big thing here. One of you will write that computer organization is invisible to the programmer. I will take off 2 points on your exam, and you'll come up to me and you'll say, "Why? Is this invisible?" No, right? If you go into an interview and say the computer is invisible, what do you think is going to happen to you?
I could do patent, right?
If you invent an invisible computer, you and I will just leave everybody behind and we'll make billions of dollars. We'll all start our own company, the Wonder Woman Invisible Computer Company on their invisible plane. So do you see why it's important not to just memorize words, but you should understand the words you're writing on your exam? So don't write invisible. Here, I'll give you a preview. There I wrote, like, unless you have a Harry Potter invisibility cloak. No. Okay, does that make sense? I think that's a fair thing to grade. All right, so 1.21, I actually defined MIPS here. A lot of this, I've posted the actual paper, not just the textbook, but in 1980, Patterson and Hennessy, they published this paper describing MIPS. Now, does anybody know who Patterson and Hennessy are?
Computer.
They are, well, once upon a time, they were computer programmers.
And they were authors.
Correct. What else? What do they do now? Any idea? Patterson is the department chair at Cal Berkeley for computer science and engineering. And Hennessy is the president of Stanford University. So that is how important the discovery of MIPS was. They basically became like, okay, you did this, you've changed the industry forever. Now you basically get to be department chairs and university presidents. Unless you take off the Mississippi, whatever they are, the IHL. Okay, so 1.22, what's the purpose of this? What's the purpose of taking this class? The main goal is the design is the high performance in the execution of compiled code. We're taking code, we're compiling it down to assembly language, we're compiling it down to machine language, and then we want it to run fast. So I probably should read MIPS. MIPS stands for microprocessor without interlocked pipe stages. So remember last class we were talking about Jack Kilby? What was the problem that he solved? Tyranny of numbers, right? So they ran across a similar problem where we're going to be talking about pipelining stages, and they thought they had to communicate all these variables in each stage. So they were interlocked. As a result, performance slowed down. So they took out the interlocking by using buffering between each stage, reduced the instruction set, and improved the performance. So it's a microprocessor without these interlocking pipe stages. And so it's a general purpose microprocessor architecture designed to be implemented on a single VLSI chip. So we got rid of these pipe stages. We have our general purpose architecture. You compile C code, Java code down, and it'll execute. They initially ran C on MIPS. And then the main goal of MIPS is the high performance execution of compile code. Okay, so as I said, when we discuss C in section 2, we'll go into more detail. So these 23, 24, and 25 are straight from the paper, but I want to read them to you, and I want you to write them so you understand it. So we have the main goal, right? So any organization you go to, they have a mission statement and a vision statement, right? So the mission statement is this is what we're doing. The vision statement is this is what we'd like to accomplish with this. So MIPS has a main goal, and then they have a basic philosophy. It's the same way. So the basic philosophy of MIPS is to present an instruction set that is compiler-driven encoding of the microengine. You will hear me say that phrase, compiler-driven encoding of the microengine, to the point to ad nauseum. You'll be sick of hearing me saying it. But it's an important thing. We are going to take C code. You're going to compile it down. So you're going to learn how to convert it to assembly language. Then you learn how to convert it to machine language. And that is going to drive the micro engine. Thus, little or no decoding is needed, and the instructions correspond closely to microcode instructions. So here's what that means. We typically, when you have some instruction, well, especially before MIPS, you'd have to take the opcode in all the different registers that we talked about and perform these complex decoding operations. What they're doing by having the instructions done this specific way is they're actually encoding the instruction simply so that when it goes into the data path, all they have to do is send those 6 bits to the opcode, the last six bits to the function, and they can perform the operation by just having it flow through the data path. So you no longer have to worry about interlocking. And therefore, the instructions correspond closely to the microcode engine, to microcode instructions. So they wanted to high performance execution of compiled code. How are we doing that? We're presenting this instruction set where you have little or no decoding. So that's their basic philosophy. And how do they do that? That's TGO 1.24. The RISC architecture is simple both in the instruction set and the hardware needed to implement that instruction set. So try to take advantage of code reuse. So for example, a multiplier is very large, but we can use a controller and an adder to reduce that area, right? Reduce both in the hardware and implement the instruction set. So basically trying to get rid of that code and have the compiler drive it. That's where that compiler-driven encoding of the micro engine. So you have the compiler have code, will come up with a code set that instead of having to have a multiplier, you can just add a number of times. So it's smaller, it's more efficient. And although the MIPS instruction set has a simple hardware implementation, for example, it requires a minimal amount of hardware control, the user-level instruction set is not as straightforward, and we'll talk about that a little later. And the simplicity of the user-level instruction set is secondary to performance goals. Again, this is that concept of good design requires good compromise. We talked about it just a little ago. How we had to have a little bit of area increase in order to eliminate race conditions, right? Same concept. You're going to see in MIPS, we were talking about the assembly language and machine language, and the assembly language was add, S1, S2, and S3, and it was add these two and put it in here. What happens is when we get to the binary, we're going to have 6 zeros for add, and then you're going to see it's going to be in a different order than the assembly language. It's going to be S2, S3, and S1. So it's going to be 15, so it starts 16, so it's 18, 17, sorry, 1, 0, 1, 1, and then, right? So this is S2, S3, and S1. So the saved registers start at 16. So 16 plus 2 is 18, 16 plus 3 is 19, and 16 plus 1 is 17. So they're in opposite order. But what we'll discover when we actually get into the data path is by putting in that order, you're actually improving the performance of the computer. So that's why they say, and the simplicity of the user-level instruction set is secondary to performance goals. So it's a little more complicated, but it runs faster. And the last one of these long TGOs, I know have a lot of writing, but I consider them important. So 1.25. Data may be operated on only when it is in a register and only load/store instructions access memory. So here's what that means. So in the MIPS data path, there is a set of 32 fast local registers that use dual read, single write memory. The cache memory and the non-volatile memory run slower than these registers. So in order to have the high performance of the execution of high performance of compiled code, you want to use the fastest possible registers, the fastest possible memory elements whenever possible. So this add instruction, these R-type instructions that I was just talking about, R-type stands for register type. And what that means is you perform an operation on two registers, like in that case S2 and S3. You send it to the arithmetic logic unit, perform some sort of operation, in that case add, and then it stores it in the local registers, which is why we say data may only be operated on when it's in a register, and then load and store instructions access memory. So number one is kind of the formal description of what I was just talking about. Repeated use of registers in a basic block of code prevent redundant load stores and redundant addressing calculations. So actually, none of you have probably taken operating systems yet, have you? Okay, so this is a big problem in operating systems. There's a concept called thrashing, where if you actually perform more swaps of memory than you're performing operations, then you're actually just thrashing back and forth between blocks and sets of memory. So that's a problem. So trying to use these repeated registers and only accessing using load store is not only improvement of performance, it's actually interacting better with the operating system. This allows higher throughput since more operations directly related to the computation can be performed. So it's just performed faster in these local copies of the registers. Now, load and store operations. How many of you have taken C++ programming? So how many of you are familiar with pointers? How many of you enjoyed pointers? A lot of hands going down. Okay, so load and store operations are actually what's physically going on in a pointer. When I teach you pointers in this course, we will also learn the physical implementation of what's going on underneath. And once you understand the physical implementation of what's going on underneath, it becomes a lot simpler to write pointers because you actually know what's going on. You know what that star for dereferencing. You know what that ampersand for the actual address actually means. And so we're going to act like, here's the proper way to write a pointer when calling a function. Here's the proper way to write a pointer. These are going to be topical guide objectives. You follow that, you'll be fine. So load operation means I have some sort of base pointer of an array and an offset. So basically, you remember we have A5. We'll call the array A, right? And then you have the fifth element, so A of 5, like this, right? What this means is find what's actually the sixth element of the array because they all start at 0, right? So you have a base pointer to the array, and you're going to have an offset that you find the actual physical value. Load word operation is going to take some sort of, we'll call it, since it's 5, we'll call it 20, S3. So this register actually holds the physical location of the base element of where the array is stored in memory, right? And then the offset is, we're going to learn about why this is, but it's going to be 5 times 4, which is 20, because it's what's known as byte addressing. So bytes are broken up into 8-bit bytes. You have 32-bit, that's 32 divided by 4, which is 8. So that actually, and then it says store load, take the value from the memory, put it into the local register S1. And store word is the opposite way. You find the base pointer and store it back into data memory. So when you have that load word, that's the equivalent of a dereference. You're dereferencing. You have a pointer to memory, and you're saying, give me that actual value to perform the operation on. And when you have an address, you're actually storing a value to a register indicating the base element of the array. Okay. So to get to part 2 of 1.25, a simplified pipeline structure has a fixed number of pipe stages. In MIPS, what we're going to learn in this course, it's 5. And we're going to learn precisely what they are here in a minute. Because stages can be used in varying related ways, pipeline utilization improves. And what that means is we're going to learn about how using pipelining you can put multiple instructions into the architecture at the same time, improving throughput and which makes the execution improve. Right. So let me scroll past 1.24 and start talking about. I can get through all the way through 126 there. All right, so there are 5 stages in the MIPS data path. We were just talking about here, a simplified pipeline structure has a fixed number of pipe stages. What are those pipe stages and what do they mean? So the first one is what's known as instruction fetch. We have instruction memory. We have a pointer. We have a program counter that points to the specific instruction I want to do. And so when the clock happens, I'm pointing to a specific instruction and says, give me that instruction. So it gets a compiled MIPS binary code instruction from the instruction memory and loads it into the data path. So step 1, give me an instruction. Boom, 32-bit instruction, like I was telling you before. So then the next step, if I have, without looking up here, I know it says instruction decode, but common sense. I have a 32-bit instruction. What do I need to do with it? Other than just decode it. Well, no, not execute yet. Before I can execute, I have a 32-bit value that's some kind of instruction. Okay? So what do I mean by decode? Understand. Okay? You need to, if I just give you, all right, do this. Like, what does that mean? Right? Then so you have to figure out what it means. Once you've figured out what it means, then you do it. Right? You actually do the execution. And here I'll actually say execution / AUG because you use the ALU. Instruction decode, it decodes the machine instruction and generates the control signals, determines the appropriate registers and memory locations, and the necessary operations to complete the instruction. So what that means is I take the 6 bits to the opcode, I send it to the controller. I have, just like the instruction I showed you, I actually select the specific registers to perform the operations on. And then I send that function to be able to determine if it's add, right? From there, I get the values from the registers that I want. I send them to the ALU. Stage 2 is done. Stage 3 is the execution. I have the control signal. I have the values I want to perform the operation on. Do it. Performs the operation dictated by the machine instruction. So data memory. So this is where we deal with load word and store word, right? Data memory. If the operation dictates it that some information must be stored in memory, it will be done at this stage. Now the reason why is we have a base pointer and offset, right? So if it's a load word or store word instruction, we're going to take that base pointer, we're going to add it using the arithmetic logic unit to get the pointer to the exact location in memory that we want to load it or store it, and then we'll do it using the data memory stage. And then finally, write back. If the operation dictates that some information must be stored in a register, it'll be done at this stage. So if it's an add, like that instruction we had before, it will circumvent the data memory and go straight back to the registers. And we use a specific control signal called mem to reg. Does it go to the memory or to the register? And so these are the 5 stages. So that covers every possible, it's actually Turing complete. These 5 stages cover every possible computing instruction you can do on a computer. And before, what you had to do is you actually had to have, when you had the interlock stages, they all had to communicate with each other. Now you just use buffers between each one. And so what happens is, once you move the instruction to the registers, and you have a buffer between them, that means you can actually generate the next instruction, right? So what happens is you have buffers between them, you can actually put up to 5 instructions in a data path at once. Does anybody have any questions about that? I know I'm throwing a lot of stuff that I will go into a lot more detail about later. But okay, so 1.27. The MIPS instruction set architecture uses an instruction format that is classified as a reduced instruction set computer. So this here, I want to differentiate between RISC and CISC. So RISC has fixed instruction lengths. What's the fixed instruction lengths of MIPS you'll learn in this course? 32 bits. Simpler, limited number of addressing modes and instruction types. And can be executed in a single cycle, therefore you can have higher clock frequencies. this becomes very important. So if you have variable instruction lengths, which we'll learn about when we talk about CISC here in a second, what that could potentially mean is that you may require multiple clock cycles to perform an operation. So sometimes, if you have a complex instruction set computer, I'll use an example. So here in MIPS, let's say we wanted to add 3 numbers. In MIPS, what we do is we add 2 numbers, store it in a temporary register, and then just have a second add instruction to do the third add, right? And then we come up with our result. If you wanted to in a complex instruction set computer, you could just have multiple types of instruction. You have a 32-bit instruction that does add 2 numbers, or you can add 5 more bits to get another register to add 3 numbers. And you could potentially require another ALU, which adds area, but improves throughput. Potentially improves throughput because you can add 3 numbers together. Sometimes in a complex instruction set, you can have multiplication. You would have a specific multiplier. The fastest one is a wall stream multiplier. Variable instruction length. It can be 32, it can be 64, it can be 46, depending on what you need. Sometimes that helps, depending on clap off. Okay. So a complex instruction set computer, RISC versus CISC. Many instructions, often several hundreds. Variable instruction length, therefore more complex. An instruction can take many cycles to execute. And so I'll talk about this last thing before we get into performance metrics. So I've been talking about these design principles, and you've heard me say this a couple of times. Good design requires good compromises, right? So there are 4. Simplicity favors regularity. Smaller is faster. Make the common case fast. And this good design requires good compromise. I'm going to scroll past RISC so people in the back can see TGO 1.28. So these are the 4, what are known as the 4 design principles. Smaller is always faster, right? What we saw in an instance where smaller and faster isn't necessarily better, right? And earlier when we were talking about up counters. Simplicity favors regularity. If you have something simple, you want to keep reusing as much as possible. You don't want your complex, slow thing to be the thing that you're constantly using. And in more detail, make the common case fast. If you have some particular instruction that you're constantly using, you don't want to have that to be your choke point. You want it to be improved. You want it to improve your throughput. And good design requires good compromise. Sometimes you have to make design trade-offs. Does anybody have any questions about MIPS, computer architectures, computer organizations, what this whole pipelining thing that we'll go into more detail about in section 7, or RISC versus CISC, all these trade-offs. We talked a little earlier about gray code. No questions? All right. So we've said a number of times so far, Objective 8 of the course is calculate the computing performance of a basic computer system, right? So performance is important. We have to run fast. People constantly want computers to run fast, and we have to worry about power consumption. We don't want it to get as hot as the sun, right? But we have to worry about the computer throughput. So the 3 in my experience, when I started out as a T at the University of South Florida, when I introduced having to know these definitions, the performance improved by a factor of 2. Like I think the problem was out of 30, the average was 15 out of 30 and went up to like 25 out of 30 just by me introducing these equations to the lecture. So execution time, the total time required for a computer to complete a task, seconds per instruction. You'll hear me say this a number of times when we talk about performance. The units will set you free. when you talk about if you're got a big problem and you might not be able to figure it out if you can't remember the equation, but if you write out the specific units of the elements that I have in the problem, you'll be able to see where they cancel out. Like remember stoichiometry in sophomore or junior year chemistry? If you use that same principle, you'll get this problem right almost every time. So throughput is just the inversion of its execution time, which is the number of tasks completed per unit time. So execution time is seconds per instruction, and throughput is the number of tasks, so that's instructions per second. And performance is 1 over execution time. So therefore, performance and execution time are the same thing. So if I have, here I have an example at the bottom here. For computer A runs a program in 10 seconds, and computer B runs a program in 15 seconds, state the improvement of performance of A over B. Now this is a simple version of the problem because these programs both have the same number of instructions, right? So if I'm trying to come up with a ratio, it would be seconds per instruction over seconds per instruction, right? Well, if the instructions are the same, it just cancels out, and then it just becomes seconds over seconds. In this case, it becomes 15 over 10, so the improvement of performance is a factor of 1.5. So B runs 1.5 times faster than A. I'm sorry, A runs 1.5 times faster than B.
How do you know which computer goes where in the ratio?
Well, here's the thing. So let's say you do it the other way, right? So I do 10 over 15, right? Here's what this means. So this is going to be 2/3. What this means is computer B executes in 2/3 of the time as, computer A executes in 2/3 of the time as computer B. Same thing here. What this means, 15 over 10, is that computer B executes 1.5 times as much as computer A. So since X performance is the inverse of execution time, that means if the execution time is more, that means the performance is less. So therefore, the ratio of improvement is I have A right here, 10, and B is 15. So by putting the one with the higher execution time on the numerator and the one in the denominator, the lower execution time, that means I'm going to get a factor where my ratio of improvement in performance comes out as greater than 1. This is actually a really good question because if you set up your equation and it becomes less than 1, what does that mean? The numerator is the one with the better performance, right? Computer A is here, the denominator. So let's think about it this way. I set it up this way where the one with the lower execution time, that means it ran faster, right? So let's say, here, I'll put it this way. Usain Bolt runs the 100-meter dash in 9.8 seconds. Dr. Morrison runs it in about 15 or whatever, right? Usain Bolt is much faster. His performance in the 100-meter dash is much better than mine, right? So the question says, state the improvement in performance of Usain Bolt over me. How much faster does Usain Bolt run the 100-meter dash than I do in a ratio? How would you do that? 15 over 9.8, right? So it's going to come out to be essentially the same thing, little over 1.5, right? So the way you would do it is you would have 15 over 9.8, 1.5. But if we did it the other way, if we had 9.8 over 15, and that's going to be about 2/3, that means that Usain Bolt runs the 100-meter dash in 2/3 of the time that I would. Does that make sense? Same thing. So let's take out away Usain Bolt and me. Let's add these scary computer words, right? So computer A, which is Usain Bolt, runs it in 10 seconds. Computer B is me, and I run it in 15 seconds. Which performance is better? Which one? Computer A, right? So, therefore, and this is the important part of the equation. Now, we'll stop here at 1.31. Let's see, TGOs 1.13 through 1.31.
Professor, that one's the 1.29.
And
1.29. Oh yeah, 1.29. Yeah, right. Yeah. If this is always I mean yes, this one was always right and this one was wrong. Yeah. It happens. So 1.13 through 1.29, and I had a couple of example questions, right? Like 1.3 and 1.4. I'll be able to figure out the answer here by going, yep. 1.13 through 1.29 and 1.3 through 1.4. Example questions. All right, so that's your homework assignment. And I will see you on Tuesday. Why are you late?
Well, I came in. I came in late for the class, but I think.
No, you haven't. Why are you late?
No.
All right, so those of you, I had a lot of people come in late today. Hold on, stop. I'm going to let you turn in, but I want to make a point here. For those of you who came in late, it depends. Typically, I'm going to hand these back, so there's going to be a 5-minute buffer. But if you come more than, once I start lecture, if you haven't turned it in, you either need to have emailed me. I had a couple of people actually email me saying they were going to be late, which is fine. But if it's a consistent problem, I just won't accept the homework, okay? Today I will. But it's got to be respectful to people who are here on time. Who else has homework?